This is work with my co-authors Bryan Parno, James Mickens, Mariana Raykova, and Josh Schiffman. And our work is about letting users access data in the data center without revealing their private information to the service provider. Maybe they don't trust Microsoft or Google, or maybe they trust them, but they aren't confident that they're completely resilient to attack. After all, we've heard stories about Chinese hackers getting into Google, into the New York Times. Employees can be bribed and infiltrated. Employees can just go rogue. Google's had at least one stalker on its payroll that we know of. And not least, governments have shown a willingness and an ability to serve subpoenas to service providers to collect private data on their citizens. So another way to look at this is a way for companies like Microsoft to protect their users against adversaries like this. But before you get the idea that because I'm talking about Microsoft and I'm a Microsoft employee that we're about to go and deploy this right away, let me disabuse you of that notion. On the spectrum of theory to practice, you're about there. So we've made a lot of progress. We've moved well beyond the theory of Oblivious RAM, but as you'll see, the performance has a long way to go before we're putting this in Bing Maps, or you can use it in Facebook or Flickr or Twitter. So one way to hide information from service providers is by encrypting it, but I'll show you that that's not sufficient. So consider David. He's privacy conscious, so he encrypts his data before sending it to his mail provider. But if he wants it to get where it's supposed to go, he's going to need to give, in the clear, the email address of the person he's sending it to, so that it can be delivered. So Outlook doesn't learn the contents of the email, but does learn that these two users are in communication. And, you know, what time they're sending each other messages, and things that maybe David and Paula would rather the service provider not know. Beyond just acquaintances, the mail providers can learn other things. There's been research showing that even if you encrypt your mail, even if you do encrypted queries, they can still learn up to 80% of the actual content of emails. And access patterns can be learned by more than just mail providers. Online social networks can learn who you're friends with. Microblogging, blogging sites can see what communities you belong to, what interests you have. Even sites that you just download content from, like a map site or a recommendation service, can learn where you likely are right now. And maybe you don't want criminals knowing that you're not at home, you're in San Jose. So the aim of Shroud is to hide all this access pattern information from the service provider. And the way we're going to do it is with a private virtual disk, a disk that hides not only the contents of blocks, but the addresses of those blocks. Let that sink in. So let's say David wanted to to send something to Paula. He will concatenate his encrypted mail at the end of block 85, the one Paula uses for her inbox. And then when she fetches email, she fetches block 85. But because that number, 85, isn't visible to the adversary, it can't link these two accesses at all. And we're going to do this assuming a very powerful adversary, one who controls all of storage, sees all of the traffic. All that he can't do is break cryptography and tamper with or see into certain trusted hardware I'll describe later. So how do we do this apparently magical thing, fetch a block from somebody without telling them which block we're asking for? Well, the theory community has something called Oblivious RAM that lets you do this. Unfortunately, these protocols are extremely slow, particularly on the large data sets that we're talking about, these data center workloads like the 30 billion or so map tiles just at Zoom level 17, or the comparable number of billions of tweets in Twitter, or the billions of photos people share with each other on Facebook and Flickr. An application of an ORAM scheme can be very slow. On average, to have all your disks working on serving one user, one map tile, would take on average 2 minutes, and in the worst case, much longer. Every 10,000 requests would take an hour and a half. Every 10 million requests, the data center goes offline basically for a week while it shuffles a bunch of data around. Okay, so our intuition here is that we can speed up Oblivious RAM algorithms by leveraging the massive parallelism that we can get access to because we're in a data center. So our main contribution is showing how we can parallelize these algorithms, how we can do that without compromising the privacy of the algorithms, how we can alleviate the I/O bottlenecks that these fixes bring about, and how we can deal with the tremendous number of faults that are likely to happen when we introduce this massive parallelism. Something I won't be able to talk about in this talk, but you can read about in the paper, is how we tolerate arbitrarily Byzantine adversaries, adversaries that aren't content to just eavesdrop on traffic, but are going to actively cheat at the protocol. So that's an overview of the talk. Here's an outline of the rest of it. First, I'm going to give you some background on Oblivious RAM. Then I'm going to just describe the design of Shroud and how we actually implemented it, and describe our evaluation of it, at which point, if you weren't aware of it before, you will be reminded of just where we are on the spectrum of theory to practice. But that will nicely dovetail in our future work section, where we describe how we might make performance better in the future, in the coming years. All right, so first background, actually a whole lot of background, because I know that Oblivious RAM is not familiar to very many of you. So I'm going to give you enough flavor of Oblivious RAM so you can follow our design. So at a high level, Oblivious RAM provides the ability to efficiently access a virtual disk without revealing which blocks you're getting. I'm just going to give you a flavor for the kind of things ORAM does. Later, I will describe an actual ORAM protocol. But the kind of thing that happens is the user has this secret key. All the data, he stores all the data on the disk encrypted with that key. Periodically, he will fetch a few blocks, locally permute them, re-encrypt them with some fresh randomness, and write them back. So now the adversary doesn't know what order those blocks are in. And after enough iterations of this, the disk is in some random order that only the user knows, and he can use this to fetch blocks from the adversary without revealing which address they actually are. Now, as you might imagine, this involves a whole lot of permuting of data. You're constantly playing this three-card Monty shell game with the disk in the cloud, and that's going to consume a lot of WAN bandwidth. In addition, the user has to keep in mind the current permutation, and that's kind of hard to keep in sync with another user, let alone the millions of users who are using the data center. So we're going to borrow an idea from Ely Evans Smith. We're going to incorporate a trusted coprocessor into the data center. It's a little bit of trusted hardware that keeps data secure such that it can't be seen or tampered with by the adversary. You can do this in a number of ways. You can leverage trusted hardware in the form of a TPM and a secure execution infrastructure. Or you can use an entirely separate component, like a tamper-resistant smart card, like I have here in my hand, or a tamper-resistant FPGA, or a full-blown PC that's tamper-resistant, otherwise known as a hardware security module. In any event, it is this trusted coprocessor that is going to possess the key, keep track of the permutation, do the Oblivious RAM algorithm with the servers, but this time over the low latency, high bandwidth data center network, and all that the users are going to have to do is convey their requests over a secure channel to the trusted coprocessor. Okay, now I'm going to delve into the details of a specific ORAM algorithm, the binary tree algorithm. This is the one we adapted for parallelism for Shroud. And there's two main reasons we chose this one. First of all, it has the same worst case performance as average case performance. So there's none of this, the data center goes offline for a week working on one request. Another thing is, as you will see, it is very amenable to parallelism. So this was first proposed by Shichen, Stefanov, and Lee in 2011, and it goes like this. I'm going to describe how it organizes untrusted storage, how it looks up a block, and how it makes sure that no two lookups to the same block look the same to the adversary who may have broken into the data center. Okay, so how is data organized? Well, physically it's an array, it's a disk or a series of disks, but we're computer scientists here. It's easy to think of that as logically a tree with log n levels, where n is the number of addresses in your virtual disk. Every node in that tree is a bucket that contains order log n blocks. When the coprocessor wants to insert data, he'll insert a block at the root. He's going to hand the adversary a big blob of encrypted bits containing the address of the block, the contents of the block, and something called a designator that we'll talk about more later. Now, because every insertion takes place at the root, before every insertion, we have to do a shuffle to make room at the root by taking some blocks and pushing them down. Now, ideally, what we'd do is we'd push down just enough to make sure that no bucket overflowed. But there's two problems with that. First, there's billions of these buckets. And there's no way to keep track with the limited memory that the trusted coprocessor has of even which ones are full. Second, the adversary is watching everything we do. And we want the adversary not to have any idea what's going on inside this tree, specifically, in particular, which buckets are full. So instead, we need to have a randomized algorithm. So every access, what the binary tree algorithm does is it chooses two random buckets from every level, chooses one block from each of them, and pushes them down. And the math shows that with high probability, no bucket ever overflows, and there's always room at the root to insert things. Each of these shuffles down takes place in view of the adversary, and we don't want the adversary to know which way blocks go. So if we want to take this orange block and move it to the right, we're going to fetch the entire bucket into the trusted coprocessor. We're going to fetch the entirety of the child buckets in. We're going to do the shuffle down internally, then re-encrypt and write them back. So the upshot is that the adversary may have some idea of how far down a block has gone in the tree, but has no idea where in any particular level it might be. So he's dumbfounded, but we need to know the organization. We need to be able to look up a block. How are we going to do that? Well, that's because we're going to use the designators I alluded to earlier. When you insert a block, you choose a random designator, a path from a root to a random leaf, in this case, left, right, right, left. And every time we shuffle that block, we're going to shuffle it along that path, unbeknownst to the adversary. So now, by just keeping in memory a mapping from addresses to designators, a few bits, we can know where roughly each block is. So the block at address 7 is somewhere along this path, and just by fetching that order log squared n number of blocks into the coprocessor, we can get the block that is needed. Unfortunately, this only works once. Once you've used LRRL to look up block number 7, you can't do it again because that shows the adversary you're looking up the same block. So what you have to do is take that block, assign it a new random designator, and then move it to the root along that path. So what are we going to do? So we can do this obliviously in view of the adversary. We had to fetch all those blocks inward. At that time, we're going to move the block to the root, re-encrypt, and then write them back. So now the adversary doesn't know which block we moved up, and the next time we access it, we're going to fetch a whole different subset of blocks. So that's enough of the binary tree algorithm that you can now understand how in Shroud we're going to parallelize it. So we make the observation that nowadays you can get high protection trusted coprocessing for very cheap. People purchase these smart cards in bulk. You can get them for about $4 each. And so you can buy a lot of them and plug them in, say, via USB to each of the servers in your data center. So now what used to be done by one trusted coprocessor could be done by many of them. We just have to figure out a way to make the algorithm parallel. And there's a lot of details about this in the paper. I'll just talk about how we parallelize lookup. It should be clear that we have to fetch all of these blocks. We can just have each block go to its own coprocessor. Each of them will have to re-encrypt them to delete it from wherever it went, and then write them back to the adversary. Now, there is a complication. By taking an algorithm that used to run inside one component and parallelizing it, we now open up a new avenue of attack for the adversary. He can now see the internal communication of the trusted device. So if a bunch of coprocessors have looked up a block and one of them has found it and needs to convey it to another one, say to insert it at the root or return it to the user, he can't just send that directly there. The adversary is watching the network. We have to have a deterministic communication pattern. In other words, we have to have all of the coprocessors sending their data to that coprocessor. And that creates a bandwidth bottleneck. It solved the privacy problem, but now created a new I/O problem. So one way to solve this is with an aggregation tree. Have pairs of coprocessors combine the blocks until only the block that needed to get through to the coprocessor is there. And this saves a lot of bandwidth. It goes from order log n to order log n. But we make the observation we can do even better. we can use cryptography to let us leverage the untrusted server. And we call this approach Oblivious aggregation, and it works like this. So each of the coprocessors that has something to communicate is going to encrypt it homomorphically. I'll say what that means soon. The homomorphically encrypted blocks are conveyed to the untrusted server, who performs an operation on them to produce another encrypted an encryption of the result. So that's what homomorphic encryption does. It allows an untrusted entity to perform an operation on items even though they're encrypted without learning anything. Now, normally homomorphic encryption is extremely expensive, but for particular scenarios it can be made quite efficient, and we made it very efficient for this scenario. All we use is a pseudorandom function. So the first coprocessor computes A1 XOR A2, where each A is a pseudorandom invocation. The next one computes A2 XOR A3, and so on. And the one coprocessor that has something to communicate, the block, will XOR in its data. Now the adversary can XOR together all these items. The A1s will cancel, the A2s will cancel, and so on. And all that will be left is the encrypted data block that needs to be passed to the target coprocessor. The adversary learns nothing untoward through this process because all of the components are completely random to him, even the one that has the data XORed in. The last contribution that I have time to talk to you about is how we achieve fault tolerance. So bringing a lot of parallelism to bear has one dire consequence, which is that faults will be commonplace. So one of these coprocessors is going to go bad. The main tool that we have to combat this is to make all the operations simple and deterministic. They get some data, they churn for a while, they produce a result, and if that coprocessor should fail, well, we'll just get another coprocessor, give it the same data, it will compute the same thing that the failed coprocessor would have computed. The only exception, there's only one exception where we cannot do this, and that is assigning request numbers to user accesses. To prevent a malicious adversary from rolling back our state, we have to have one master coprocessor keep track of how many accesses have happened so far and tag each access accordingly so that they can be matched to the proper states. Because this is stateful, we can't simply rely on determinism. We have to replicate the master coprocessor and accept the word of a quorum of master coprocessors that a certain user request is assigned a certain access number. We only rely on a quorum so that if one of the master coprocessors fail, we can continue to operate. Of course, as master coprocessors fail, you run the risk that a quorum will become not unavailable. So we also have something called delegation that allows a quorum of master coprocessors to take another coprocessor and delegate responsibility to it that used to be the responsibility of the failed coprocessor. We have a proof of this a full proof in our tech report that this is correct and secure. So we have actually implemented this on these smart cards that I hold in my hand. So we wrote C code that runs on these and some C# code that runs on the untrusted server. These are very resource-poor devices. They have slow CPUs, very slow I/O, about 12 kilobytes per second, but they're cheap, and they provide provable tamper resistance to FIPS level 3. We only have 10 of them that Infineon gave us. So to simulate greater scale, we built an emulated smart card that we can plug into a real server. And to simulate even larger numbers of coprocessors than that, we built a simulator that we validated against the prototype. We're going to use the workloads that I just alluded to earlier, the billions of objects in various workloads. We also have a small-scale workload for when we only have 2 to 8 coprocessors churning on something so that our experiments do not take weeks to years. So the main result is that our application of parallelism allows us to achieve linear speedup. And that may be visible from this graph, or it might be a little easier to see if I invert the axis. You can see that as you increase the number of coprocessors, you can clearly leverage that. This trend continues as you add more coprocessors. We can emulate out to 128 coprocessors and still see a linear gain. And the simulated results show that this continues much further. You can up to about 10,000 coprocessors, you get near linear speedup. Only after about 10,000 coprocessors do we run out of things to do in parallel. So the upshot is that we can bring the time to perform an ORAM access down from days to seconds. So that's a lot of orders of magnitude reduction, but unfortunately, the absolute performance is still quite poor. It is probably not acceptable to have all of your disks churning for 9 seconds just to serve one tweet to one user. And he probably doesn't want to wait 9 seconds. Somebody probably, even worse, does not want to wait for 45 seconds to get a single map tile, or, heaven forbid, 4 hours to get a Flickr photo. So, what is the cause of this? The cause is the bandwidth bottleneck. These things are very slow. They have 12 kilobytes per second of bandwidth. So although for small block sizes, we're dominated by the cost of shuttling around constant-sized things like attestations and Merkle hashes, for the large objects like Flickr photos, we are suffering the consequence of 12 kilobytes per second. That leads us to an understanding of where opportunities for future work lie. We're pursuing several ways to make Shroud faster. So what we have learned is that what matters less is the absolute cost of these devices, but rather the amount of bandwidth you can get per unit cost. So an alternative to smart cards is to use FPGAs, which cost more, about maybe $100 to $200, but can offer substantially greater bandwidth on the order of 3 gigabytes per second. Another different way you could go is to abandon the need for physical security. So suppose you only care about hackers who break into your data center over network channels, or employees who only have remote access to the physical disks on which and computers on which the service is running. Then you can use AMT, you can use the secure execution infrastructure, leveraging the TPM, and thereby get bandwidth equal to the full memory bandwidth of a PC class machine, about 12 gigabytes per second. Yet another, even further out approach that we could do is to expand the notion of what is a trusted device. Typically, trusted computing embraces just the CPU and memory within the trusted computing base. But what if you could also admit the disk? This will take a lot of work in verifying the correctness of the low-level disk code, as well as all the system software on which that disk code relies. But if we can make disk accesses trustworthy, then we can use much more efficient Oblivious RAM protocols that assume a large amount of memory on the trusted coprocessor. But again, you're compromising on physical security. If you don't want to compromise on physical security, FPGAs are the most promising way to go, and we've done some initial simulations. They suggest that at modest cost, in the scale of a data center, for about $10,000, you could get bandwidth down to, latency down to about 10 milliseconds. So, to conclude, encryption is a powerful tool for protecting the privacy of user data in the data center. But it is not sufficient. It can't protect the access patterns to that data. To protect access patterns, you need techniques like Oblivious RAM, but unfortunately they are very slow. We've shown that they can be dramatically sped up by orders of magnitude by applying parallelism, although that opens up new cans of worms, such as fault tolerance and I/O bottlenecks, and ensuring the privacy of algorithms even when the adversary can see your internal communication. So this work has discussed solutions to that problem, and in future we want to consider how to find higher bandwidth trusted components to make the performance even more reasonable in the future. Thank you. I will now take questions.
Hi, Mark Lilbridge from HP Labs. Isn't your Oblivious aggregation just the dining cryptographer's protocol?
Okay, sure. It is so I guess there's one subtlety that is a little bit one subtlety. Well, never mind. Never mind illustrating the subtlety. Often in this particular case, you wind up. Another challenge here is that you have to produce data that is attested. And in our particular scenario, it is acceptable to produce the data in this fashion because the data can be self-attesting. Anyway, thanks for your comment.
Go ahead, Dave. I think you want
So, Dave Anderson, Seagate, there are trusted drives that essentially have FIPS 140 approved code protection and built-in logical smart cards. You might think of using something like that.
So I was one of the reasons why I wanted to present this work to this forum is because I have heard about work on trusted disks, and I want to learn more about that. And hopefully you recognize that this is one of the potential applications for that. So please, I'd like to talk to you more about that.
John Kachuk with Cray. So back to the previous question about the dining cryptographers.
Okay.
Query or problem. The mere fact that the cryptographers are sitting around a public table leaks information. And you're promoting an idea which is a hard level of encryption, but if someone's going to really go after data, they're more likely to attack the weak link. So that's either on the person's desktop or the network interconnects and the relationships between the two people that are communicating to the data center, not necessarily the data center itself. That
is certainly true. That is yet another reason why this is research about the future. So it's trying to protect against even more privacy than is necessary nowadays because there are much weaker links. However, privacy is very important to people. There's a lot of us and a lot of you doing research in ways to secure all these other elements of the user's infrastructure, and so eventually this will become the weakest link.
Quick question.
Is this on? Oh, okay. This is to make me trust Microsoft more. Why am I going to believe they actually deployed all these expensive smart cards and didn't just lie about it?
So so there are two answers to that question. So first of all, the attestation, the secure connection that you make to the data center is secured with a certificate provided not by Microsoft, but by Infineon or Intel or AMD, the manufacturer of the hardware. And so the user can readily tell, well, if the media can readily tell whether Microsoft is actually deploying this. The second answer to the question is, even if users do not care, one of the purposes of this, as I said, another perspective on this work, is Microsoft may want to just protect itself. And so in that respect, even if no user ever checks, it's still useful for us to have that running in an isolated environment that can't be hacked.
Actually, I think we're going to have to cut off there.
Just one quick one. Will you be able to respond for lawful warrants for the information?
So one of the purposes of this work is to not be able to respond to lawful warrants.